All right, so today's lesson 1-4 in the algebra book. Today we're going to talk about graphs. We're going to graph kind of different situations and then talk about the domain of those, which, if you can see by your definitions, are all the values that may be meaningful when substituted. So specific to the context that we're talking about, we may designate different sets of numbers as the domain, numbers that make sense for the situation. And we're going to be putting them on graphs where individual points are plotted for different situations, and we could refer to that as a scatter plot. So jumping right into different sets of numbers, some of these will seem familiar and some of them may be new. So whole numbers, we consider our counting numbers. So our whole numbers are going to be 0, 1, 2, 3, 4, on and on and on. So pretty much any number, we're not including negatives, so all your positives. So examples of these, that's going to be, anything, 100, 20, and 1. Any whole number, including 0, those are our counting numbers. Integers now are going to add our negatives. So it includes negatives. So examples, -3, +2, 0. So all of those are integers. Sometimes students get confused and think it's just the negative numbers, but that's not necessarily true. So really it's all of your whole numbers and their opposites. So 2 and -2, 3 and -2, but we also include 0. So real numbers, this includes your wholes, integers, and all the numbers between. So think about what numbers are between these. You're talking decimals and you're talking fractions. So you're talking about like the number 1.2 or 1/2. It could be a repeating decimal, 3.4 repeated. Could be numbers like pi. These are all real numbers. And then positive real numbers are obviously the same as these. So actually we should include a negative up here. So let's do like -2.7, right? So here now it's just going to be obviously the positive ones. So it's all numbers that are positive. So again, 1.2, 1/2, 3.4, pi, just no negatives. So up here we can add another negative, -3/4. Just so we're clear, real numbers is positives, negatives, fractions, decimals, everything. And obviously your positive real numbers are just the positive versions of that. So when we talk about domains, we're going to try and put these sets in to represent the domains. So here we go. Example number 2. Rebecca's driving 500 miles to her grandma's house and she averages 65 miles per hour. We're going to fill in the chart that kind of shows us the remaining distance after a certain number of hours. So when she hasn't started driving yet, 0 hours, the remaining distance is obviously 500. That's how far she is. So now, after 1 hour, she's knocked 65 off of that. So for our calculation, it's going to be 500 minus 65. So that's 435. Calculation for the original, there is none really. It's just starting at 500. Now we're going to have to write a pattern. We're going to write an expression for this. So when we actually start to subtract another 65 for hour number 2, we're going to write it as repeated subtraction. So instead of starting with the 435 and minus 65, we're going to show that it always starts with the 500, and we're going to subtract it a certain number of times, and it's going to match how many hours it's been. That's going to help us build the pattern here. So we minus another 65, that's 370. Minus another 65, that's 305. And one more time, 4 hours of driving, 65 miles each hour is going to leave us with 240 remaining. So you can see here's the calculation. Every single time it's 500 minus some number of 65s. So our pattern is going to be 500 minus 65 times however many hours it is, because for 1 hour it was 165, for 2 hours it was 265. So you're going to take 65 and multiply it times how many hours. That gets subtracted off 500, and that's your remaining distance. So your pattern here, for this one, you had 500 minus 65 times 4. So if you multiplied 65 times 4 and then subtracted it, it's the same as subtracting 65 4 times individually. So it's 500 minus 65 times 3, 500 minus 65 times 2, 1. And even here, 500 minus 65 times 0, that would just be 0, so you have 500. All right, so the whole point of today now is to take this and put it onto the graph and then come up with a domain, so a set of numbers that represents the hours of driving or whatever it is in each situation. So I'm going to bring my sheet in here. You're going to have to flip yours over, but I want to keep the chart on the screen here as we go through this. So we're going to create our graph right here, and we kind of want to see time happen from left to right. So instead of putting the hours up and down, I want to see time passing this direction. So the bottom is going to be my hours. And then this is going to be my remaining miles. So I'm not just going to put miles, but we're talking about how many miles are left. So that's my remaining miles. So we're going to start at 0. And now my chart just goes 1 through 4. So I could just go 1, 2, 3, 4, but now all my data is right here. So I'm going to kind of spread it out. I'm going to go every other. So I'm going to go 1, skip, 2, skip, 3, 4. And if we kept going, there's a 5 and a 6 and 7 hours. Now, remaining miles, we got to have 500 on there. So we could go by hundreds, 100, 200, 300, 400, 500. But now half my graph is just empty. So instead, let's go by 50s, or just keep skipping. And there's 100, 150, 200, 300, 400. That puts 500 right here. Let's go back and label 100, 200, 300, and 400. All right, let's put our data on the graph now. So we're comparing the 0 to 500, the 1 to 435. If we were going to write these as points, this is my x-axis and my y-axis. So my x is my hours. So it's 0, 500. It's 1, 435. 2, 370. 3, 305. And my last ordered pair is 4, 240. So those are your ordered pairs. Those are the coordinates that we're going to put on here and create a scatter plot. So this will be a scatter plot once we put points on it. So 0, 500 is going to be right on the axis at 500. 1, 435. We kind of have to estimate this is 450, so a little under. 2 and 370. A little under 400. 3 and 305, so just barely over it. You can start to see this is consistent, right? This isn't going to go down fast or go up fast because she's driving at a consistent speed. It's the same 65 miles per hour, so that should form a nice straight line. And 4 is 240, so here's 250 and a little under. And you could start to project where this is going to go as you move forward. Okay, so we connect these dots. And we could keep going. It's going to look something like this. Okay, we can predict how many hours it's going to take her. Now, we can't always connect our lines like this. Depends what we're talking about. And our next graph, we're going to look directly at that. But you can't just put 1 hour, 2 hour, 3 hour, because she has the option of going a half an hour or 45 minutes or 51 minutes. Right? And she'd be a different distance. It's not like you have to go exactly 1 hour, 2 hour, 3 hour. There's all that time between it. So we have to connect the dots. If we were just putting the dots, we're saying there's only the option to go 1 hour or 2 hours or 3 hours, nothing in between. So we want to measure everything. So we're going to connect it. So what is the domain of variable h? What is the domain? So we can't just say, if we go back up here, we can't just say integers, because that means it's all whole numbers, 1 hour, 2 hour, 3 hour. And again, that would look like dots on the graph with no line, nothing connected. So this is everything in between. Now, domain is always talking about our x-axis here. So we're talking about the hours. So what represents the hours? You could say real numbers because, right, you can have a half an hour or 1.2 hours, but we're not going to have negative hours. Okay, so this domain here for variable h hours is going to be our positive real numbers. And notice it says explain. Okay, and so you can say it can be a decimal or a fraction. That's why we chose real numbers. Can be a decimal or a fraction, and it can't be negative. So that's why we specifically said positive real numbers. So positive real numbers on a graph are going to be represented by a solid line, no negatives. Real numbers are going to be a solid line, and they can be positive, negative, anything. Integers are only your whole numbers. So integers on a graph, even if they're in a straight line, are not going to be connected. Same thing for whole numbers. They're just not going to go in the negatives. So no negatives. So they're going to look a little bit different. So the real numbers are the ones that are connected because every number in between, fractions and decimals, count. But your integers and your whole numbers are going to look like just dots. You can't connect them. It has to be the whole numbers, no fractions, no decimals. So let's see what that looks like in example number 3. We slide this up. All right, so this table shows the values for the term n and 1 plus 3n, which, kind of going back to a couple sections ago, we're going to use it thinking about the number of toothpicks in the nth term. So we had those squares with the toothpicks. This was one of the patterns that we looked at. We're going to fill in the table using this pattern. So you're going to substitute the term number for n. So this is going to be 3 times 0. This is 3 times 1, 3 times 2, 3, and 4. So our calculation here is 1 plus 0. This is 1 plus 3. 3 times 2 is 6. 1 plus 9. And 1 plus 12. So our total number of toothpicks, term 0, so we're starting with 1 toothpick. Term 2 has 4 toothpicks. I'm sorry, term 1. Term 2 has 7 toothpicks. Term 3, 10. Term 4, 13. All right, so we see the pattern. Gives me a rate of change of 3. That's why it's the coefficient to the variable. So this is increasing by 3 toothpicks every single time. So let's put this on the graph and let's see what it looks like. So we're going to put the terms across the bottom, starting with 0, 1, 2, 3, 4 is as far as we went, so that's fine. This is the term. And then going up in this direction, this is going to be the actual number of toothpicks. And if you count, we've got 12 lines here if we go straight up from 0. So if we want 13 to be on it, we'd have to kind of change it up. But for the sake of this exercise, it's okay if 13 doesn't fit on the graph because we just want to talk about what kind of numbers these represent. So let's just count by ones. So again, we're only going to get to 12. So let's set up our ordered pairs here. So it's 0, 1, that's the term number and the toothpicks. 1 and 4, 2 and 7, 3 and 10, 4 and 13. So let's put this on the graph. So term 0 is at 1. Term 1 is at 4. 2 at 7. 3 is at 10. And then again, we can't fit 4. It would be up here off the graph. Now, before you go connect this, I think your first instinct is going to be to draw this line. Let's think for a second. Does that make sense? Is there a term half? Is there a term 1.7? No, in this specific situation, there's only a term 1, a term 2, a term 3, and a term 4. There's no halfway to a term. Okay, so we can't connect this. There are no values in here. You're not going to have a piece of a toothpick for half a term. That doesn't make sense. Okay, there's just a term 1. You add a certain number of toothpicks. There's term 2, certain number of toothpicks, term 3. So we are not going to connect this line. It wouldn't make sense because then you're going to have partial pieces of toothpicks for a partial term. Again, doesn't make sense. So what are we representing here? Well, this is going to be for your variable n, which is our term. What domain represents it? So you can't say real numbers. We can't have halves and 0.5s or any of that. Okay, and we're not going to have negative terms either. Okay, so this is going to be our whole numbers. And again, it says explain. No negatives, no fractions or decimals. That's why we chose whole numbers. So I'm always going to ask you to explain why you chose the set that you chose. So you need to be able to back it up. You can't just guess. Why whole numbers? Because there can't be negatives with our terms and there can't be fractions.